Hello and welcome back to Calculus 1, section 2.7, precise definition of limits. So finally we get to define the limit, which was done about 150, 100, maybe 200 years ago, something like that. I think 1850 was the year when this was done. 1850, so 170 years ago. So calculus was already there. Newton 200 years before the limit definition put down all of the ideas for derivatives, and then Riemann worked on definite integrals and integration in general, Euler as well. So, calculus was well established for the most part. And then one thing that it's actually used to explain everything well and better than these guys did is the limit. And now we're going to take a look at the definition for the limit, see what it's all about, and we'll go from there. So assume f of x is defined for all x in some open interval containing a except possibly at a. So limit x goes to a of f of x equals L. That's the notation, and we say if for any number epsilon larger than 0, there is a corresponding number delta larger than 0 such that the difference of f of x and L is smaller than epsilon whenever x minus a is in between 0 and delta. This is the definition. And what I want to do now is explain what this all means. Before we do that, we have these two Greek letters that you might not have seen so far. Epsilon is equivalent to our E, and the delta is the lowercase d. So technically just E and D if you want to translate those letters in Latin alphabet from the Greek alphabet. You have seen Greek letters before. You've seen pi, right? For instance, seen theta, maybe alpha, beta, and gamma. Depending who you took pre-calc 2 trig course with, you definitely see them in my class. But so you know quite a few letters. You will also use lambda and mu and rho, and as you go through math courses, we use a lot of Greek letters because Greeks figured out a lot of this stuff, 2,000 years ago. So we have these two numbers, epsilon and delta, E and D, and they're both extremely small values, as small as you want them to be. So 0.000000000, and you put as many zeros as you want / need in there to make them as small as you need them to be. So you have two small numbers, very small numbers. They're both positive. They're larger than 0, but they're still very small. And now what we do is we draw the picture which explains the way this definition works. So we take a function, there we go, f of x, and we pick somewhere to have our a and to have our limit L. And now we make this tube around it. And this top one will be L plus epsilon, L minus epsilon. And on the x-axis you have A minus delta and A plus delta for these points here. So the idea goes this way. If you are to squeeze here, you take your fingers and you squeeze in, because they have to follow, the corners over here have to follow the function, you will get a squeeze over here and it will squeeze into L. So, and it goes the other way as well. So technically, this idea of f of x minus L, f of x minus L, if this is your f of x value and here is your L value, then the difference, sorry, not that, this is not this is L plus epsilon. You pick a value in between, some x value in between, and that x value, maybe I should have done that in blue. There we go. So this part here is f of x minus L. That little distance in there is f of x minus L, which is this much, and this much over here is epsilon. So you see that difference there is epsilon, and you can also see here on the bottom, oh sorry, this side, right here is x minus a. And this whole thing here is delta. So x minus a is smaller than delta, and f of x minus L is smaller than epsilon. And those are very, very, very small. The more you squeeze, the more it falls on L, and L is the limit. Remember how I said that limits do not compute at a point? And you would say, well, wait, we learned the plug-in technique. Yes, we learned the plug-in technique for convenience. But remember, all of your limits can be solved by the first method we learned, which is the chart method, where you pick the values going closer and closer and closer to the x you want to compute, and eventually, right, those are your answers. So there is a squeeze. You can see that this a plus delta, right, you squeeze it into closer, which is x, then you can squeeze even closer and closer and closer and closer. So x minus a is getting smaller, 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 and it's always smaller than delta. The delta corresponds to epsilon, and the distance between f of x and L is also decreasing. They're all smaller, and they're getting smaller So they're getting to these values. So you really have to think about this, and you know, it's easier when you see my fingers, right? But we are not in a classroom, so I can't do that other than, you know, to put these black arrows. But as you squeeze on those red lines, and as those red lines are collapsing to the black line, the top red lines are also collapsing to the black line. And they will go through stages, and that one of those stages is the blue stage that I have there. And that blue stage is the arbitrary stage that we use in the picture, in the equations over there, that is for our definition, right? And what it means for the limit not to exist. So we can use our good old friend 1 over x, if my pen worked. This is literally the last picture I have to draw for the day, and the pen is deciding not to work. Oops. So here is the good old friend 1 over x. And let's say I want to check what's happening here as the limit of 1 over x as x goes to 0. Well, here's my, if this is my a, then this is a minus delta. And as you can see, it gives me this value here. And if I go to the other side, let's say here, then I have this value here, and this is a plus delta. So the delta is the increase. Now remember, the two values, as I squeeze, need to collapse into the same point. Over here we said that as you use these squeeze over here, as you squeeze, they squeeze here into L, because the top one squeezes down and the bottom one squeezes up, and then they collapse into L. Now look what happens here. If I am to go in and make a new one, a minus delta blue now, and a minus delta blue, a plus delta, you see how they're further apart now on the y-axis? They do not get closer, they do not share a point, and because they are not doing that, there's no limit. So limit does not exist, and you see that this one is shooting this way, this one is shooting that way. They do not collapse into the same y value, and because of that we say, hey, there's a vertical asymptote there, right? Because they shoot to infinities. And you also see that, right, you can't divide by 0. So it's all of those concepts from the past kind of click in together. And now you hopefully understand how and why all of that is happening, because you have the definition finally. And that's it. So you are responsible for the definition, and the two pictures, one explains the limit, the other one explains limit does not exist. And those are the two. Bye.